Right, so welcome back. If you recall, we talked about the Nash equilibrium and what actually constitutes machine learning. I'll just spend maybe 2 minutes on. So I've taken it from a recent book by Sinha et al. 2020. You can actually see the complexity and the time progression of machine intelligence and maybe what is the most dominant algorithm, right? So as I mentioned in the previous session, the things started maybe 1956. So you can see neural network. So there would be an AI winter. Then we are talking about AI Spring these days. So you have deep learning algorithms. But the future would be we are looking for super intelligent machines. So machines which can allow us to meet uh, their action should be such that they achieve our optimal objectives, right? So they just don't achieve any their objectives. They should not just achieve our objectives, but they should achieve our optimal objectives. So they actually sense the environment and decide what is the best action for us, right? So we need computability of that order. In fact, this could be highly philosophical. I don't want to spend too much time on that. Looking, the course objective is the focus is more on manufacturing. But if you are keen, uh, maybe look at Church Turing cases, right? I'll close the machine intelligence part. Certainly, I think each of these algorithms, like deep learning, you can actually see courses on that. Certainly, that's not something which I really want to emphasize as part of this course. But what would be relevant for me to actually see how the blockchain as a technology can help the manufacturing context. Right. If you recall, we talked about the manufacturing objectives, which was again the flexible, cheap, diverse, and better and sustainable also. So five objectives there, and the for supply chain also, I think these are the five important primitives. What is what goods are moving, right? Who is the buyer or who is the seller, right? Where it has to go, where to locate. Then two things: where things move, how things move, right? So you talk about logistics, and where things sit. So you talk about inventory, right? So these five primitives becomes the part of supply chain, and each of these aspects offer respective insights into different risk in supply chains. So this these so I think I mentioned in the previous sessions that the supply chain of a company like Intel, they could not trace the supply chain beyond 2 or 3 years when the Japanese earthquake came in 2011, right? So what it actually brings is you are looking for traceability, compliance, and visibility, right? So I can trace from where that material is coming. I can trace, so I want that all the compliance part should be taken care. So a lot of regulatory requirements may be there, right? So you can think of even um, Tesla recently announced that they want to come up with a zero cobalt battery. And the main objective is because the cobalt supply chains are still not fully traceable, right? So if there is a compliance requirement that it should come from ethical sources. So let me also add that a large number of cobalt supply chain, the origin goes to Congo, and you would actually see a lot of child labor is involved there. So we want that all those things should be avoided in the supply chain. So you want traceability, you want compliance, and you want where the goods are sitting, how much is the delay, what are the quality issues. So all those things should be visible. So these three things becomes part of the story of the modern supply chain management. And I think we extend this argument to digital supply networks also. right? So these are some of the risk. So COVID times, you would see a lot of discussion on resilient supply chains, right? So can blockchains allow us to make that? Can blockchains allow us to achieve that, right? So natural disasters, you can think of intentional disruption, accidents. So I'm pretty sure if you start mining, you would relate to a lot of examples like this. So where you see a lot of risk which comes in achieving these supply chain objectives. Now, I'll go slightly deeper into that, right? So, when we talk about supply chains, when we talk about blockchains and supply chains, so distributed ledger is something which most of people associate when we talk about blockchains, right? So, we are talking about now network. There could be a network where so you can think of a network something like this. So these could be nodes, right? And some of these nodes could be miners also. So what they do is, so they actually gather blocks of transactions and they actually compete to verify them, right? So I think I'll explain all these things. And in return for their service, so miners that successfully verify a block of transaction achieve both an allocation of newly created currency. So for a distributed ledger, I give you an example. Like if you have to transfer a money to some other bank account, right? So a request you send to your bank, the bank will give it to a centralized ledger, maybe sitting in the RBI, and then it is verified that you actually have that money, and it will be transferred to the other bank's account, right? So it is done through a centralized ledger, but now we are actually saying there is a distributed ledger. So all these nodes could be part of the distributed ledger. So in this case, the verification is not centralized, it is in the distributed manner. Only thing you have to ensure that no single node is powerful enough to change the ledger, right? And that is where all this part auditability, immutability, and disintermediation comes in, right? It means that you can easily verify. It should not be immutable. It means no one else, one person can be powerful enough to change that thing, and it should not be centralized. You want no intermediation there, right? So you just want that everything should be distributed. And this actually, you have to come up with some kind of a mechanism where you achieve all these things at the same time, and that is where the whole notion of blockchains comes into the picture, right? So as I mentioned that we use some ideas of game theory. In fact, the main idea of game theory is to avoid this cheap talk, right? So distributed ledger, in fact, we sometimes call blockchains. So blockchain and cryptocurrency could be, you can say cryptocurrency could be a subset of blockchain, right? Was made possible by the emergence of many innovations, which include the internet. So it rests on concepts from cryptography, game theory, and peer-to-peer networking, right? It is a fully decentralized payment system. So I'm now emphasizing only on the Bitcoin's part, in which copies of the ledger are shared between all participants, and a process is established by which users agree on changes to the ledger, right? So to make that transactions valid, right? And since anybody can check any proposed transaction against the ledger, this approach removes the need for a central authority and thus for participants to have confidence in the integrity of any single entity, right? And so how it is done? In fact, this problem is coming from the medieval times. It is called as the Byzantine journals problem. So people in computer science may be aware of this. But uh, the main idea here is that it should be decentralized and no single entity have the power to change the ledger, right? So as I mentioned that uh, we use ideas from game theory, and we call it a cryptographic proof of work, which ensures that the agents who are the miners should not be involved in the cheap talk, right? So let me see whether I have put that thing. Yeah, I think so. This example we already have seen as part of our game theory discussion, that uh, uh, players can communicate to each other that we are going to play T comma L, but when the game is played, you again converge to Nash equilibrium, right? So you want to avoid this cheap talk of communication, which is T comma L. So you want to come up with some kind of a mechanism or an incentive mechanism which ensures that you don't do this cheap talk, right? And that is where this cryptographic proof of work comes into the picture. Uh, so maybe I'll explain it in the subsequent slides how that thing works, right? So let us take this as a network. Now, there all this A, B, C, D, E, F, these are the nodes in that network, and all these nodes are connected. Uh, um, all these nodes are well connected. Now, there is a transaction which is happening between E and F. So this red line you can actually see as part of the transaction, and D, G, and I are the miners in this case. So the whole ledger actually sits on at three different. In fact, it should be available on all the other nodes also, but these are the miners, right? So what they do, they actually do the verification of this transaction whether A actually has ample money which can be transferred to F, right? And so there would be history of how A achieved that money, and that is also part of the ledger, right? Now all this information come as part of blocks, right? And you cannot change a block unless or until all the miners agree that it can be changed, right? So it means that they actually have to come up with some kind of a consensus to change the ledger, right? Now the point here is whether they can actually do the cheap talk. To avoid that thing, they actually have to spend some time in so normally what is the value of the hash? So it's more like a puzzle for them, which can actually be done by trial and error, right? So the puzzle is developed as part of the network. It follows some kind of a Poisson distribution, and it takes about 10 minutes to solve that puzzle, right? So on an average, that's the mean time, right? And once you solve it, you communicate to all the other nodes in the network, right? So there is a, and then, so if it turns out to be correct, your puzzle turns out to be correctly solved, then you will actually be paid for it, right? Now, this creates some kind of an incentive problem because you actually have to spend, and you may not be the only one, and the complexity of the puzzle actually keeps on increasing. That is actually part of the architecture, right? Now, the point here is that it is not, you can say, cheap for you to just communicate something that this has been verified. You have to spend something, some effort has to go, and you need computing power, right? So all the other nodes are competing because you are actually paid for it, right? So you want to do it as fast as possible and let others also do the verification. And let me also add that all these nodes are anonymous, right? So in fact, the example which we are giving is of the public blockchain. So there would be permission blockchains also. In fact, I think Unilever actually implemented the permission blockchain as part of the digital supply network. In this case, we are talking about a public blockchain, and in this case, all the nodes are anonymous, so you don't know where that replica sits, right? So this actually solves this problem of uh, the incentive to avoid the cheap talk, right? So uh, uh, so you can actually see, you can think of an example where so I'll give you, so we are going to talk about public-private key cryptography, right? And so what happens is, if you assume that uh, you have to do a transaction from one person to other person, right? Like in our case, from A to F. So F may generate, let us start with F, right? So F will generate a pair of public and the private key. right? So private key will stay with F, and this public will go to A, and he will attach uh, the digital signature, and it would actually come back to F, right? Now, even if someone knows the public key, they cannot actually generate the private key out of it. But from if you know the private key, you can generate a public key. Okay. So one public and one private key. So even if you know the private key, you can generate the public key, but the converse is not true, right? So even if the public key is known to all the other agents, they cannot verify what is the, or they cannot generate what is the private key, right? So this is something. So I'll give you an example how this whole thing work, and I'll take maybe a simple example which can illustrate this idea of what I'm saying of the public and the private key. So let us take two agents. One is Alice and Bob, and assume that they have to do some transaction. Correct. And I'm giving this analogy of paint mixing to make a sense of what we are saying. Right. Now, Alice decides uh, uh, a color which is the public color. Right. So when I say public color, so it means that that color is known to everyone, including Bob. Right. But then there is a third party or third agent, which is Carol, and they want that the transaction should be hidden from Carol. So she cannot make out what actually is the transaction, right? So, but this color, which is the public color, which is green, is known to all the agents, right? So Alice and Bob announce that this is the public color, and Carol also can observe it. But at the same time, uh, Alice and Bob, they also have a private color, right? So that's their choice, which is not revealed to even to Alice or to Carol, right? So Bob decides red as a color, which is the private color. Alice decides blue as the private color, and that is not revealed to anyone, right? Now what she does is Alice, she mix this private and public color and get a private public mixture. This is, let us for say, Alice. Bob also does the same thing. He mixes his private color with the public color and come up with a private public key pair, which is for Bob, right? And let assumes that he puts, so let us say that there is a center place where they put this mixture, right? So Bob comes and put the mixture in the center. Alice comes and put the mixture in the center, right? But that private color is still not revealed, right? Now Bob comes and take the Alice mixture and add with his private color. And Alice comes and mix the Bob mixture with her private color. Now what we will see, right? So it contains red, blue and green. It contains red, blue and green, right? So both will know, they need not to know what is the private key, but they actually make out what was the final mixture. Both will get the same thing, right? So this is the main idea of this public private. And Corel, even if she knows, even if she picks any of those colors, right? Even if she picks the mixture also, she does not know what to mix with that, right? So she may not get the same color what actually has been achieved by both Bob and Alice. And that is the main idea of the public private uh, 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 cryptography, and that is part of the blockchain, right? Now only thing is, so this transaction is between say A and F. Someone has to do the verification, and that verification, so as soon as this is done, this becomes as part of the block. And as I mentioned that you can add or you can edit a block only when you do this prove this cryptographic proof of work. and which comes at a cost, right? So this you can actually see in this slide. So there is a latest block. This is the miners block, right? And then this nonce value you have to uh, estimate, right? Hash value less than the threshold, yes. If no, you keep on trying, right? And blockchain is becoming a general purpose technology. It lowers the transaction cost. So you relate to that idea of Ronald Coase, right? Through costless verification and without the need for costly intermediation, which improves the efficiency and scope for markets, moving them closer to a direct peer-to-peer ideal, right? So a lot of things about the transparent visibility, right? All these things, compliance, all these things comes part of the blockchain, right? So in this case, we are in fact calling it a distributed ledger technology or a trustless consensus engine, right? So everyone converges to that consensus, and remember that we are not calling it trustful, we are actually calling it trustless, right? I need not to trust other person, but I trust the technology because I know that the technology is robust enough that you cannot actually change anything unless or until everyone agrees for it, right? So miners candidate block will be changed only when you solve this puzzle, and that is not cheap. It is expensive. You have to spend some energy, some resources to achieve that, right? So that forms the basis of this. I hope you got some idea about how these things work. And as I mentioned, that what they are achieving is they are reducing the transaction cost, and which may lead to a different kind of organization altogether. Right, so I'll give you some examples for this. I think this will give you some idea, right? So there is in fact a company called Provenance, right? They are actually tracing the food supply chain. Okay, so you can see that you can actually trace the whole origin of a food product till the consumption, and the technology of blockchain is becoming the benchmark for it. So a large logistic company like Merck's and IBM, they actually have come up with a trade lens blockchain shipping solution, and uh, they want that industry-wide collaboration. It is announced in Jan. Advances as more than 90 organizations participate in the great global trade solution, right? So they really want to improve the traceability, they want to improve the compliance, they want to improve the visibility. So all these things are becoming part of um, the digital supply network, and that certainly would have implications for manufacturing also, right? So I'll take another example, which is the Walmart Canada, and they have come up with a blockchain-based supply network, which is similar to the for free tracking and payment, right? So I give you the numbers. They operate they own in fact 2,100 trailers and trucks, 70 carrier partners, and they transport over 500,000 loads of inventory to about 400 retail stores across Canada, right? And it is estimated that about $150 billion per day of supply is tied up in the supply chains in US for invoice disputes, right? And that is where I think the Walmart Canada initiative of implementing a permission blockchain with 27 nodes, right? So this is different from a public blockchain. So in permission, you allow who should be the miner, right? But the incentives may be very similar, and so for an organization like Walmart, I think the permission blockchain seems to be a better option than going for a public blockchain, because you may actually sometimes see a lot of spurious activity in the public blockchain, right? So blockchain ledger connects to legacy systems such as ERP accounting systems and transportation management systems. So that has been already done by Walmart. So this is something interesting as an example that how they are actually integrating. So other example which comes is from Unilever. So Unilever is a company which is co-headquartered in London and Rotterdam in Netherlands. They own about 400 brands, sales in about 190 countries, and the revenue is about 50 billion globally. And you can actually see that if you read this, uh, this plant makes dough, soap, and ice cream, and this is a joint offered by Unilever and Microsoft to actually establish a virtual factory to tune up its supply chain. And what they are doing is they're actually using AI or machine intelligence, connected devices, harness a stream of data to keep production moving and reduce the cost, right? So in fact, they come up with the digital twin to replicate the physical system. We already have talked about that. And they want to actually make their production more efficient. They are looking for convergence of technologies like IIoT, cloud, ML, right? And just to give the context that they have launched 8 more digital twins in factories across North America, South America, Europe, and Asia. And they want to name it digital rewiring, right? So Unilever is already doing that. So I've taken this as part of a Wall Street report. Other company which is doing uh, as part of manufacturing is Caterpillar, right? And they come up with something called as a live factory. So they are converging. So you can actually see this, right? So you, in this case, we are talking maybe about a machine. You put a sensor on the machine. You track the movement within the factory. You remove the sensor, and what it actually does, it maps the movement, location, time spent at different processes, and the quality summary also, right? So the quality defects. So in fact, just give you the numbers. So this is a kind of a dashboard which comes as part of this live factory. So it is called as manufacturing common operating environment. You can actually see the defect count, defect per unit, right? The new live factory was able to identify $12 million to 18 million in savings as reduced latency, automated activities, right? And they could actually reduce drastically the inventory cost by $1.2 million, labor cost by about $500,000. Right? So this has come as part of implementing this live factory where you are actually converging on all these solutions. So you can actually map not just outside, you can do it within the factory. You can optimize your resources. So the main idea of sensing, collaboration, and optimizing can be seen as part of Caterpillar. Okay, and they have integrating made be with a typical SAP system. Right. So if you look at mass, you can say personalization. So two companies are at the forefront. One is Nike and other is Adidas, right? So Adidas, in fact, have come up with 3D printing solutions, and you can actually see there is a big change in that, right? So we started this whole course when we talked about manufacturing in China. But now what is happening is this high-tech factory is bringing the production back to Europe, right? So you can actually print it closer to the customer, and this customization allows better matching of the demand and supply also. Okay, so as I mentioned about Nike, you can actually see the quotation. One day consumers will be able to buy a shoe design file from Nike. So you're not actually buying the shoe, and you can actually print the shoe themselves. So that is the kind of innovation you would be looking in the context of manufacturing, right? So we want more customized, more personalized, at least for the apparels and the shoe, that thing is true. The company has established partnerships to build a 3D digital design system to transform its product creation process, enabling capacities such as digital print applications and rapid prototyping, right? So they have actually brought 3D printing as part of it. And they've established the House of Innovation at different cities, right? This is in Shanghai. And they are actually calling this approach as always on approach. So you are actually closer to the customer, you are customizing the products, and the point here is it is the convergence of all these technologies, right? So you are not just about the data analytics, you are integrating it with the manufacturing process also, right? So in the future, what the Nike former CEO is claiming, you would actually see that is true for not just shoes, it may be true for many other products, right? So this brings me to the closure of this session, and this also brings me closer to the closure of the business part of the future of manufacturing. The future sessions would be taken by Dr. Chandrasekhar and would be on additive manufacturing, right? So I hope you enjoyed this discussion. Thank you.